Hey, my name's Scout. This is going to be the demonstration for the third Fluent project. I'm going to do it in two parts where I kind of go over the geometry and the mesh that I'm using for all of the cases, the inviscid flow, turbulent, and the laminar viscous flows. But first, we're going to get started. We're just going to drag this Fluent module over here. Nope, I don't want that. That was from the component section. Delete that. Go over here, Fluent, and then we can add. I'm gonna go over here, geometry, make it 2D, and then we can go over here, right click that, and then new design modular geometry. Okay, cool. So now we're in the design modeler. First thing we're gonna do is make sure we're looking with the z-axis behind us. We go over here, click sketching. Then we can make a circle. Start it at the origin here. Just make sure. And then we'll do that. I'm gonna put a dimension on that for the radius. And I'm gonna make that a 1/2 meter so that the diameter of this cylinder, which is what the circle is gonna represent, so that the diameter is 1 meter. It makes the calculation a lot easier. And then we can back to sketching. We're gonna draw a line up here, straight up. And we're gonna put a dimension on that. Vertical dimension, just click this top point and this point. We have V2, we're gonna make that 25 meters. We're just making it far enough so that any friction with the walls isn't gonna affect the flow that we have around our cylinder. But yeah, we can go to sketch again. We're gonna make another line. Try and get that horizontal. It's gonna be going this way. And then we can go here. I gotta put a dimension on that, horizontal. That's gonna be another 25. And then let me just make sure that these two. Yeah, so those are gonna be the same. So those are the same height. And then now what we can do is go ahead and go draw, make a rectangle starting at this point, and make it go down here. And now we can put this dimension on it, so we know that the distance between these is going to be 50 meters, should be. And now we can go ahead and put another dimension. So this one's going to be going from here to here. And this one should be 50 meters as well. Awesome. So now we have this kind of sketch going on for us. Next thing we're going to do is go to concept and then surface from sketches. And then we're going to go ahead, go to box select, and do this. We're going to hit generate. Okay, that is not what we wanted, actually. We're gonna delete that. Because that's just in the center of our circle. We're gonna go ahead. There we go. We finally got the one that we wanted. We just needed to search around a bit, which is pretty much all of Ansys, for me at least. But now that we have this, we can finally leave, close Design Modeler. And now we're going to double click on Mesh over here. So now that we're in the meshing software, we can go over to Mesh. We can just click on that. We're going to go ahead and insert method. Click on the surface, apply. Want to do triangles. We're also going to go ahead and add an edge sizing on, click over here so that we can select the edge on that. And make sure capture curvature is off. And the behavior is hard. And then, yep, good. And then we're also going to do a inflation on this boundary. So on this boundary is going to be that. And then the one I used was this. I made the first layer thickness 0.01. I think I left it at 0.1. Make sure you put the max layer is like 100. And then that should do it. Now we can go ahead and generate. So I tweaked with the mesh settings a bit, but what I ended up with is for edge sizing, I have 200 divisions, no curvature, and hard behavior. For inflation, I have my first layer thickness set to 0.002, 100 maximum layers with a growth rate of 1.1. And then for the method, I just did all triangles and then surface here. And so this is what it looks like after generating that. You see we have this fine mesh by the surface of our cylinder, which is good because that's what's important to us, how the flow develops over that cylinder. So now we can go ahead and close meshing, and then we can go to setup. I'm gonna hit double precision. I'm gonna run 5 processes, and then hit start. So the first thing that we'll do is go over to models. We're going to change this from SSTK omega to inviscid for our inviscid flow. And then we can go over to boundary conditions, go to our inlet. double click that, and then make the velocity 5 meters per second per the assignment. And then we can go down to reference values. Let's just check this, make sure everything looks right. Yep. Length is 1 meter because that's our diameter. Depth is 1. Area 5 meters per second. Yep, everything looks good. The next thing we're going to change for this inviscid model, we're going to go to a simple scheme. And then for pressure, it's just going to be presto. This will just make the calculation run quicker. But for initialization, you can go initialize 10. I'm gonna do 25 because I was having some trouble with the inviscid flow earlier. I just want to make sure everything is good. But hit initialize. And then we can go to run calculation. Double click that. Hit number of iterations. It's gonna be 1000. And then go ahead and hit calculate. So the simple, like I said, that method is going to make this process run a lot faster. And I think our residual value is like 0.001. So right about now, yep. So now that we've done that calculation, we can go over to graphics. We just want to check that everything looks right. Let's do coefficient right here, compute. And then, yep, everything looks symmetrical. So we know we did this right. Let's just check out the velocity really quick. And yeah, everything's symmetrical, which is what we're looking for with this inviscid flow. So yeah, now that we have this, we'll go over to the results tab. Oh, sorry, let's open that back up really quick because we got to do a few things before we head to our results. So I'm just going to head over, run that computation again so we can have the results. And now we're going to go over here to the XY plot. We're just going to check this really quick. Pressure coefficient on the cylinder, and then the x-axis is going to be our direction vector. Let's go ahead and plot this. And so this looks right. We can see that the pressure coefficient is 1 at the start of our cylinder, so at the negative 0.5 relative to the center. You can see that. And then as we go getting closer to the top and the bottom of it, the pressure coefficient drops to -3 and then heads back to 1 again whenever it reaches the other side of the cylinder. And so we can export that by writing to file, which is what you would do if you're completing this project. I've already done that part, so I'm just going to go to the next step, which is plotting the velocity variation. So we're going to do the same thing, basically, velocity magnitude on the surface of the cylinder. We're going to plot that, and we get this. So the velocity is 0 at the front of the cylinder, which makes sense because there shouldn't be any velocity there. And then as we go up here, it reaches 10 meters per second, which looks right again, which is twice the free velocity of the free stream velocity of the air. And then it goes back to 0 as it reaches the other side of the cylinder. Yep, so all this looks right. Now we can go over to the results tab. So I had those from earlier, but basically I'll show you how to make them. For the velocity contour, you're gonna go here. So contour. The location is gonna be symmetry 1. The variable is gonna be velocity. And then I'm just gonna set the contours to 100 so that we can see the details. But then we can see this, and everything's symmetrical, which looks right for the inviscid flow. And then now we can plot the streamlines. So we go over here. We're gonna start from inlet so that they go outwards like from this way around, we can see what's happening. Equally spaced. I'm just gonna do 50 out on it, and we can do this. Let's get rid of this contour, and now we can see the streamlines. And this also looks right. We can see it just kind of goes around and then right back. It's super symmetrical. Everything looks right for our inviscid flow. So now we're gonna go ahead and look at our laminar viscous flow. But instead of making a whole new mesh, we're just gonna do this, transfer data to new fluent, and then we can just adjust the setup conditions. We don't have to do anything like make a whole new mesh because we already have the one that we need. So we're gonna go to setup here, double precision, 5 processes. Yeah, that should be good. So now that we're in here, we're gonna go over to models, change it from K omega to laminar. We're gonna go over to boundary conditions, double click on our inlet, and then we're gonna set the speed to the one I use. Found that works with 0.2. Hit apply, and then we can go over to, let's go to materials, air. One thing I did change, I changed the viscosity to 0.001. A lot of trial and error that goes into this. I found out. So this is the one that I found works though. So we're gonna go close. And then let's go to reference values, check everything's correct. Compute from inlet, surface body. And yeah, length 1, density, 2, viscosity. Everything looks right. So now we're gonna go over to initialization. Hit hybrid, let's do 25, and then initialize. Now we can go down here, hit run calculation. We'll just say 1,000 iterations, and then calculate. So that calculation is complete. Now we can look, make sure everything looks right. We got contours. Let's look at the velocity here for all these, compute. And yeah, so this looks pretty good. We can see this long wake region, which there should be for the viscous, for a laminar flow, has that long wake region with low velocity. And then we see here that the velocity is very small, and around the entire surface there's 0 velocity because of the skin friction, like the no slip property. And then you can see this splitting occurs very early, whereas the inviscid flow just went around like that. And then now we're gonna check the pressure coefficient magnitude, or we're gonna go over to plots, XY plot, and then we can do the pressure coefficient around the cylinder. And yeah, so this also looks pretty good. We can see it has that high pressure coefficient where the pressure would be max at that low velocity area, and then it goes like this. And then we can also do the same thing for velocity magnitude, say plot. And this also makes sense because as we saw on the contour, all the velocity on the surface of the cylinder is going to be 0 for any viscous flow because of the no slip condition. Oh, and another thing that we got to look at, we're going to go to forces. We can get the ones on the cylinder and then print this. And so this is how we're going to see our drag coefficient. So over here you can see right here, this is going to be our total drag coefficient, 0.835. And then now we're gonna go ahead and check out the results for this. And to do that, we're gonna have to go over here to component systems and then go to results, and we're just gonna connect that to this solution here. So viscous laminar results. Double click this. Z-axis here. First thing we're gonna do is make that velocity contour. Location is gonna be symmetry 1, velocity, and then we'll do 100. And you can see here, this all makes sense. This long wake region behind the cylinder, and then this kind of stagnation right here. And then let's check out the streamlines. So we can go here, automate, start from the inlet. Let's do 100 this time. And then variable velocity, hit apply here. Let's turn off this contour. Yep, and this is exactly what we want to see, this long wake region. But yeah, so now let's go ahead and do our turbulent simulation. So we're going to do the same thing here, transfer data to new, fluent. We're going to edit this setup. Double precision, 5 processes. So now that we're in the CFD solver, we're going to go over to the model, change it from, actually we're going to keep it on the K omega because this is the turbulent simulation, and I could not figure out how to get the laminar flow to work without it creating these weird wake regions. So we're going to go here, keep that, like I said, materials. We're going to keep everything the same for air. That's what I found what works. We have this 1.7894 for the viscosity, keep those. For the boundary conditions, we're gonna go over here, change our inlet. We're gonna set the velocity magnitude to 100 meters per second. And then the next thing we're gonna do, we're just gonna go over, check our reference values, make sure everything looks right. Yep, yeah, 100 meters per second, right viscosity, density, everything looks good. So the next thing we're gonna do, get over to initialization, set it to 25 again. Okay, initialize. So now that is complete, we're gonna go run calculation, do about 1,000 iterations, and hit calculate. So now our calculation is complete. We can go over to graphics. Let's make sure everything looks right. Let's do pressure coefficient, compute, and then display. And yeah, so this looks right. Let's see status, or the velocity rather. And then we can kind of do this, compute. And then yeah, so this is about what we want to see. We have the no velocity at the front, the no velocity around the entire edge from the no slip condition, and then this smaller wake region than the viscous laminar flow. which makes sense because the turbulent flow should basically keeps it sticking to the surface for longer, which makes this region smaller because it's coming out of here instead of up here, like we saw with the viscous laminar flow. But now that we have this, we can go over to our results. So let's close this. Now we're going to do the same thing, just drag a results tab over here, connected to solution. Double click this. So now we're going to plot the velocity contours up here. We can go location, symmetry 1. Let's do velocity, 100 contours, and then let's flip it. So now this is what we see, which is what we just looked at in the solution. But yeah, the smaller wake region, the delayed flow separation on the edge here, when compared to the laminar flow simulation. And then let's go ahead and plot our streamlines. So we go over here, and then start from inlet again. Let's do 50 this time. And then velocity, yep, everything looks good. Get rid of that. And then now we can see, yep, everything looks good. The smaller wake region for the turbulent flow. So yeah, we can go ahead and close this now. Oh, one thing I forgot to show you guys, I'll grab the drag coefficients for the, let's go to solution. But I'll grab the drag coefficients for the turbulent flow and the inviscid flow as well, because I forgot to do that. So we're just going to go to the solution tab, wait for this to load. We can go over to reports, forces, hit cylinder, print, and then this is where our drag coefficient is, which we can see is a lot smaller than our viscous drag coefficient, which makes sense because, like I said, that wake region is smaller due to the delayed flow separation and the turbulent viscous flow. But let's go ahead and check out the inviscid flow drag coefficient, which should be 0. Fingers crossed. Let's just go ahead and refresh. Should be 0 because there's no skin friction. Everything's symmetrical and there's no wake region. So let's see what we can do. Wait for this to load. So now that we're in here, go down to reports, forces, and then cylinder, print. And yeah, so it's not going to be exactly 0 because it's not perfect, but it's going to be damn near close. So we have that 0, 0, which makes sense because there's no wake region, no skin friction. So yeah, I think it makes sense. But that is my demonstration for this project. Hope you have a good night.